Greetings, everybody. It's a Friday, not that it matters because you're watching a video here, but wanted to get some of the solutions to these FRQs down. And, well, this is one of those 25-point qualitative, quantitative FRQs, so I'm probably going to spend about 25 minutes going through it, but that's going to include some description and maybe not all of the writing that would be required. So this one right here is from the 2019 administration of the AP Physics 1 exam. This is the actual question given on the test. And it says that you got a block A on the tabletop connected to a string, to a massless pulley connected to block B that's hanging down there. And whenever I read these problems, I just gave you a quick summary there, but whenever I read these problems, I always want to basically take everything out of that paragraph and remove it if it's useful and write it next to the diagram or write it to the side, because 25 minutes seems like a pretty decent amount of time, but when you're trying to solve a problem, you run out of time quick, and if you have to keep going back to a paragraph and try to remember everything, it's going to be a waste of your time. So here it says that exploring the relative masses of the two blocks and how it affects acceleration of the blocks. Block A of mass MA, so go ahead and write in MA next to that. Well, that's kind of a given. As it rests on a horizontal tabletop, there's a negligible friction between block A and the countertop, or the tabletop, sorry. So we can go ahead and say that there's no friction. Negligible means you can neglect it without any problem. And block B of mass MB is hanging over from light string that runs over a pulley attached to block A as shown above. The pulley has negligible mass and spins with negligible friction, so the pulley just goes. It's not going to require any sort of energy to start moving. It's a mythological situation. It doesn't actually have any friction. Now, on the first part here, this is a qualitative, quantitative problem. Some of it's going to ask you just to think in terms of ideas without any equations whatsoever, and that's the first questions. It says for A, part 1, or I, suppose the mass of block A is much greater than the mass of block B. So mathematically, we could write that as MA is double greater than, meaning much greater than, the mass of block B. And they want you to estimate the magnitude of the acceleration of the blocks after release. So you'd imagine that MA on the tabletop is 100 kilograms, and it's like a human being, right? Like I'm 90 kilograms or more maybe. But it's a lot of mass up there, and even though it's on a frictionless surface, it's still a lot of inertia. And if MB is like a paperclip, well, the weight of a paperclip trying to pull a whole human being, even on a frictionless surface, probably not going to do much. So they say estimate of the magnitude. That just means ballpark. So you could guess a number, but why guess a number when you can say that it's pretty much close to zero? So for this problem, when they say an estimate, and specifically afterwards they say briefly explain your reasoning without using any equations, you can't come to a numerical answer without equations unless you know it's in free fall. So we just say it's close to zero. Go ahead and put in the units there. Briefly explain your reasoning. Well, if you've got something hanging over the tabletop that's small, you'd want to say that says without using equations. You'd have to say that the weight of block B is attempting to accelerate the total mass, scroll here, which is much greater than the mass of block B. Yeah, no equations. So I can't put m times g, I just have to use the word weight to represent that. Now for part 2, they're asking you to kind of flip it around. What if the mass of the block B is much greater than the mass of the block A? How is that going to affect the problem? Well, it should be pretty much the opposite. If you had a human being hanging on a rope and over the pulley there's a paperclip sitting on the table, you can imagine that that paperclip is almost like it's not even there. And in that case, the block of that mass equivalent to a person would accelerate pretty much in free fall. So you could say that's close to 9.8 meters per second squared. You could say it's close to G, close to free fall, but something along those lines to let the College Board people know that you understand that it's pretty much an unrestricted acceleration. So let's write that down. And I'll go and put in parentheses G here. Briefly explain your reasoning without deriving or using equations. So it's kind of along the same lines as what you had before, but now you just kind of flip it. So I'm not going to write all that in here, but I'll leave it to you to be able to come up with a coherent sentence that allows them to know that it's a lot of weight and not a lot of additional inertia. Now let's take a look at part B. Oh, part B, this is lovely. It's just a diagram, free body diagram. Free body diagram where you of course draw all the forces, not components, no sines, cosines, or anything like that, of real actual pushes or pulls on the block. So only actual pushes or pulls. There's always a tendency for people to want to say, well, the velocity is going this way too. Well, yeah, it is. You know, for the block A on the tabletop, if the whole thing is going around, then yeah, the velocity is going to go that way, but that's not a force. It's not a push or a pull. That's a speed or a velocity. If you have real pushes and pulls, then you want to include those. So on block A, even though it is not affecting the problem one way or another, there is a weight force, Fg, acting on that block. And the tabletop is resisting that weight force with the normal force. And even those two balance out and we don't have to calculate friction or anything, those two do exist. There's also a tension force. I'll call it Ft, because that's the way we typically do it, although you could write just a capital T. And then for block B is going to have its weight force, and it's going to have the tension force going up. And that's that. Those are the free body diagrams. If you did not include the weight force and the normal force on block A, you're going to lose some credit there. Got to include those. All right, now we get to the parts with some mathematics. We could use equations and stuff. Part C says derive an equation for the acceleration of the blocks after release in terms of ma, mb, physical constants like g, as appropriate. If you need to draw anything other than what you had in part B, do it below. Do not change your answer to part B. That's a big no-no. They only grade you based upon what you have in a section, and if you add stuff to it for later work, they're going to assume that that's what you wanted for your answer for part B. Part D says consider the scenario from part A2 where block A was much less than the mass of block B. Does your equation for the acceleration of the block from part C agree with your reasoning, yes or no, and kind of go through those steps. I'm realizing now that I did forget something that's written here that's very, very important, and that is this statement at the top, which just caused utter confusion with people last year. It's not a situation where block A and block B are wildly different masses anymore. Now, neither one of them is much greater than the other, but they're not necessarily equal. So it could be like 1 kilogram and 0.9 kilograms, or 1.0 and 1.1. Like they're similar, but not necessarily the same. That's an important thing for down below. And then in part E, they're asking you if the pulley was replaced with one that did have mass, which means that it has a rotational inertia and it requires some torque to get it going, how would the tensions in each half of the string change? So we're going to go through these three parts together here. We'll start with part C, but I just want to preview what all was there. For part C, it says derive an equation. Now there's a couple ways of doing this. One is to use the actual free body diagrams, which is the more appropriate and kind of long-handed way to do it. And then there's sort of the shorthand version that we've used in class before. I'll set it up both ways. But in terms of net forces, if we want to take a look at each block individually, block A has a net force acting on it in the direction of motion, which would just be the tension. Nothing else, just the tension. And then that would equal mass times acceleration for that block, which would be ma times the acceleration, lowercase a. And for block B, the net force that's controlling motion would be in the vertical direction. And in that case, we would have tension minus mb times g. And if you have those two forces acting against each other in the vertical direction, they're still going to produce an acceleration on the object, or potentially. And in that case, we would want to include the negative sign to show that that would be accelerating down, not up. So that'd be negative mb times a. Now we could do a simultaneous solve here. We could substitute in ma for the t and then do some simplification. And when you do that, you should get that the acceleration is going to be equal to mb times g divided by ma plus mb. Now that comes out of algebra. You just do the algebra there, substitute solve. But an alternate way to think of that, which we did back in the beginning of the year, was to just sort of take a look at what forces are ultimately fighting against each other to try to make this thing move or not move. And we would say that that would produce some net force along the sort of dimension of motion. And then we would divide that by the total mass that's actually in motion. And in this case, we've got the weight force pulling down on mb, but there's no friction on top. So the net force trying to drive the motion is just mb times g. And the total mass that's in motion is the two things that are there. So ma plus mb. And if you look, that's the same exact result. So a couple of different ways of looking at that. All right, let's go into part D now, where it says, consider the scenario from part A2, where the mass of block A is much less than the mass of block B. Does your equation for the acceleration of the blocks from part C agree with that reasoning? So if we were to take the equation here, and of course the answer is going to be yes because we're perfect, and then we want to briefly explain it. But if we take, and for this brief explanation, I'm just going to draw it up to the side here. If MA is much smaller than MB, then in our equation that we've got there, MA is pretty much negligible. So we can say that it is dominated by MB in the equation. So if we got acceleration is equal to MB times G over MA plus MB, then the MA that's in there is kind of like zero. Like that's kind of the limit, right? And so we can say that if that statement is true, we really just have MBG over MB, and those cancel, and you get G, which is free fall. So we can back up mathematically what we said in A part 2. Likewise, if MB was very, very, very small compared to MA, then MA would dominate the denominator. And if it dominates the denominator, then you're going to have a small weight divided by a really, really big mass, and that will give you approximately 0. So for part E, we have, they're asking us about tensions now. And it says, while the blocks are accelerating, the tension in the vertical portion of the string is T1. So when the two things were moving, the tension right here in this vertical portion of the string, we're going to call that T1 now. And after we've denoted that as T1, it says the pulley of negligible mass is replaced with a second pulley that is not negligible. It means it has mass, it has inertia, it's going to take energy to make it rotate, it requires torques. So when the blocks are accelerating in this scenario with the new pulley, the tension in the vertical portion is called T2. So we're the same string, but we're just now calling it T2. It's like the second tension. Not like object 1, object 2. It's the same rope, but in two different instances in time. And how do those two tensions compare to each other? So if we take a look at the equation we had here for part C, we can go back and kind of retroactively call for block B, the hanging block that has the vertical string on it, we can call that tension 1 when there was acceleration 1. Well, what if for part E here, which by the way, part E is one of those, hey, you got some extra time left, you didn't use up all 25 minutes yet, and here's a really hard question that's only worth a couple points. So these are not the type of questions that you start the problem with. You try to get the fundamentals done first. So for the new situation, we would have tension 2 minus mbg equals negative mba2. So we're just replacing the new acceleration, we don't know what it is, with the new tension that's vertically there. So in this case, we would have to ask ourselves what's the same and what's different. The mass mb is the same, g is the same, mb is the same. So it comes down to, are the accelerations of the systems the same? And if they are, then, well, the tensions are the same. Then there's no difference from T1 to T2. But if the accelerations are different, then we're going to have a different amount of tension in the rope. So let's go ahead and rewrite these equations down below here. I'm going to write it as T1 equals mb times g minus mba1, just rewriting it in terms of tension. And then tension 2 is going to be mbg minus mba2. So it really comes down to tension is a function of acceleration. That's the variable. And if you have a situation where now the pulley has some rotational inertia, it's not equal to 0 anymore. That means that just like if you roll a marble down a ramp, it doesn't get down there as fast and in as little time as you think it should, because you gain rotational kinetic energy as it rolls down. So the overall linear acceleration, the translational acceleration, is less than it should have been otherwise. So in this problem, if you got to make that pulley rotate, that's going to suck up some of the energy that's stored in the system, and that means you're not going to get as much velocity out of it in the same time, which means that is a smaller acceleration. So A2 is going to be smaller than A1. And if that value is less, you're going to be subtracting less from the weight, which means tension 2 is going to be bigger. As long as you state that the acceleration is the way it's stated there. Now, if you wanted to, say that the accelerations stay the same, then you can logic that and you can get some points out of it. But this is the correct answer. The alternate way to think about it is just, if I've got the string there and all it's doing is trying to pull the weight on the table, then there's going to be some tension required to make that happen. But now if I have to rotate the wheel or the pulley and pull the block, that's going to require more tension to make all that extra stuff happen. That's an alternate way to write it, but it's not going to be as good for the AP test. Anyways, that's this problem.